Okay, good. So we are ready for the second talk of today. Professor François Murat. Okay, you can go on. And sorry, just a remark, it seems that today people are more encouraged to ask a question, so please stay in the 50 minutes.
Sorry?
I say that the people seem to be encouraged to ask questions today, so let us leave the 10 minutes for question anytime.
Okay, I will try to do that, but in any case, you will stop me, okay?
Okay.
So, hello everybody. Nice to be with you again. And so I continue what I did, what I began yesterday about the about the homogenization of the Neumann's brush problem. So the Neumann brush problem is the equation which is here, which is minus divergence of A gradient U epsilon plus C U epsilon equals F in a brush omega epsilon with the Neumann boundary condition on the boundary of the brush. And what is the brush? The brush is, okay, sorry, is there. So, as yesterday, you have only to concentrate on the 2n equals 2 case for the picture, because the case where n is more than 3 is the same. So we have a set omega prime, which is a set of Rn minus 1, n is more than 2. This set, on this set omega prime, we build a cylinder. This cylinder has vertical boundaries, a below boundary sigma b, above boundary sigma a, and this is omega. Okay, omega is divided in two parts by the graph of the function psi 0, which is the interface sigma 0, and this interface separates omega a and omega b. Omega a is here, omega b is there. Okay, so we know omega. What is omega epsilon? Omega epsilon is made of two parts. The basis omega b, which is fixed in the sense that it does not vary with epsilon, and the t's, which are above the omega b, which are cylindrical and vertical, limited by sigma 0 and by sigma a, and all the set of all those t's is called omega a epsilon. Okay, so naturally, in some sense, when epsilon tends to 0, the size of the teeth is, the diameter of the teeth is always less than epsilon. And in some sense, omega a epsilon tends to omega a. Let me make now a few remarks that I didn't do yesterday, and 3 remarks actually. Okay, the first one, maybe this is not the most important one, but this is something which is interesting, that there is not any assumption of periodicity of any type in the disposition of the teeth. The teeth can be absolutely arbitrary. Okay, they can be there is no regularity of the boundary of the teeth. They can be adjacent. They can be they can share part of their boundary. they have only two conditions. The two conditions is that two different T's does not intersect, and that the size of them is the size of the cross-section is less than epsilon. So, in particular, the teeth are not assumed to be all of the same diameter. Okay, we can have some teeth of diameter epsilon, but also for epsilon fixed, some other teeth of diameter epsilon 2 or epsilon k for every k. So we can mix at the stage epsilon, things of size epsilon, epsilon 2, they have only to be of size less than epsilon. Okay? And last remark, the framework that we are able to work with is very general. Really, the only limitation is the fact that the teeth are cylindrical and vertical. And here, of course, but here, the fact that theta is greater than theta 0 strictly positive, but as I said, we are able to remove this hypothesis in the new work that we did with Antonio and Olivier. Okay, so what I want to do is to pass to the limit in the Neumann brush problem. Okay, so omega, very important, omega epsilon is a brush, as described before, and more exactly in the variational formulation of the problem, which is, okay, the fact that the solution belongs to each one of omega epsilon, and we have the integral over omega epsilon of A gradient U epsilon gradient V epsilon plus C U epsilon V epsilon is equal to the integral over omega epsilon of F V epsilon for every V epsilon in each one of omega. So this is a classical variational formulation, and this problem has a unique solution because the matrix is coercive and the coefficient is more than gamma, and alpha and gamma are strictly positive. And the right-hand side is in L2. Okay, I will now define the homogenized problem to be able to explain the homogenization result. So the homogenized problem is defined as follows. Okay, we define a new space. This new space is called V of omega, and it's made of function V which belongs to L2 of omega. That means function which can be split in two parts, VA defined in omega A, VB defined in omega B, and VA will be in L2 of omega A, VB is in L2 of omega B, and this is the same as saying that V is in L2. Okay, on VB, we assume that, okay, the function of V, of capital V, are such that gradient of VB belongs to L2 of omega B to the power n, which means that UB is in each one of omega B. While for the function VA, which is in L2 of omega A, we only assume that the gradient, the vertical derivative of VA is in L2 of omega A, and this is the fact that VA is in the space that I introduced yesterday, H of, okay, sorry, VA is in H of omega A dxn. Okay, and then those two functions, the one VB, which belongs to each one of omega B, and the VA, which belongs to each of omega A dxn are gluing on sigma 0 by their trace, and I will explain just in 1 minute what I mean by that. But this is the fact that on the intermediate surface sigma 0 between omega A and omega B, the two functions have the VA and VB have the same value. Okay, now the homogenized problem is defined as follows. So this space is a Hilbert space for the natural norm, and the homogenized problem is to find U which belongs to V of omega, such that for every V which belongs to V of omega, we have the following equation. Okay, the integral over omega A of theta A0 gradient, okay, vertical derivative of UA, vertical derivative of VB, plus the integral over omega A of theta C UA VA. Okay, so just a remark, theta is the density of the teeth in omega A. The characteristic function of omega A epsilon tends to theta in L infinity of omega of Rn minus 1 weak star. Okay, and A0 is a coefficient which belongs to L infinity and is greater than alpha, and I will define this coefficient in just 1 minute. So the problem at the beginning is not the same as before, because the term which was here, the integral of the A gradient U epsilon, gradient V epsilon on omega epsilon, is now at the limit replaced by a degenerate term, okay, or at least a degenerate term as far as the gradient is concerned, because in omega A, the full gradient has been replaced by the vertical derivatives. Okay, this is not the case for the second part of the equation, which is conserved in omega B. And the right-hand side is slightly modified, because in omega A, the right-hand side is theta, the integral over omega A of theta FVA. Okay, let me make a few remarks. So, first of all, theta appears in each integral of omega A, and you can see that. Theta on omega A, you have theta. In this term, which is on omega A, we have theta. In this term of omega A, we have theta. But there is no theta in omega B. Okay? Second thing, a new coefficient A0 appears in omega A, and the problem is degenerated in omega A, in the sense that the full gradient D is replaced by the vertical derivative dxn. No change in omega B, as I said, and we need now to define the coefficient A0 and the traces gamma at A and gamma B. I do that now. If you believe me that V, with the definition of the traces, V is an Hilbert space, the homogenized problem has a unique solution. This is a non-classical problem, because this is a transmission problem between omega A and omega B. In the above part, we have a degenerated problem because only the vertical derivatives take place. And in the below part, we have a classical Laplace equation for a classical Laplacian. Okay, So let me define the coefficient S0 in omega A, and also some vector function zeta, which will play an important role in the proof. Okay. For that, I write the NN matrix A in blocks, like that. So here you have a block n minus 1 by n minus 1, which is A prime. You have a vertical vector V prime, which is in L infinity of omega to the power n minus 1, an horizontal vector which is in L infinity of omega to the power n minus 1, and the last coefficient, ANN, which is in L infinity. Okay, so alpha prime, which is a submatrix, a block submatrix of A, is alpha coercive, and the equation A prime Z prime plus V prime as a solution. This solution is just zeta prime equals minus A prime minus 1 V prime, okay, with where zeta prime is in L infinity to the power n minus 1. We define S0, which belongs to L infinity, by this strange formula. S0 is equal to ANN, the last coefficient, plus H prime zeta prime, the vertical, the horizontal vector and the vector zeta prime, which is nothing due to this formula than ANN minus H prime, A prime minus 1, V prime. And so we complete the Z vector, the Z prime vector is the vector in L infinity of omega to the power n minus 1. We complete this vector by 1 at the last place, and we get zeta prime, a vector zeta, which is in L infinity of omega to the power n. Okay, let me observe that if I compute head zeta, okay, by block, this is easy. I find two components, and the first component is 0 due to the definition of zeta prime, and the second component is exactly S0. And if I form A zeta zeta, this is A zeta, which is here multiplied by zeta, which is zeta prime 1, so this is S0. But since A zeta zeta is more than alpha zeta square, this is more than alpha zeta, this is equal to alpha zeta prime square plus 1, so more than alpha. So the coefficient is coercive, as I said before. Note that the coefficient S0 and the function zeta, do not depend on omega and omega epsilon. They depend only on the matrix A and no more. Okay? Now I define the traces on sigma 0. Remember that omega A and omega B, okay, sorry, let me do that in another way. We have sigma 0, which separates omega A and omega B, and omega here is a cylinder. Okay? So, since UB belongs to each one of omega B, UB has a trace, a classical trace, gamma B, which belongs to each 1/2 of sigma 0, the intermediate, the upper boundary of omega b. Okay, this is when omega prime is smooth. But when omega prime is not smooth, this is only in each one half log of sigma 0 when the set omega prime has not a smooth boundary. Okay, so this is okay for omega b. We understand what is the trace. Okay, so there exists for each one of omega b, sorry, there exists a trace operator that I call gamma b, which put each one of omega b in each one half of sigma 0, if omega prime is smooth. If omega prime is not smooth, this is each one half log. For HA of omega A, for H of omega A dxn, there exists also a trace operator that I call gamma at A, which put H of omega A dxn in L2 of sigma 0. Okay, and this follows for a very simple formal computation, which is the following. We write formally v of x prime 0 minus v of x prime L is the integral from 0 to L with a sign minus 1 of d over dxn v of x prime s ds. Okay, this is classical. Okay, changing v, multiplying v by a function which is 0 for xn equals L, this term disappears. I can put that to the square, that to the square, and integrating all of that over omega prime, I find this line, the integral over omega prime of v of x prime 0 to the square is less or equal to the integral over omega prime of the square of this integral. I make Cauchy-Schwarz in this integral, and this square here is estimated by L square, the integral of 0 to L of d over dxn v of x prime s square, which means that if I write that v square in L2 of sigma 0 is less than L square, the vertical derivative of v in L2 of omega. Okay, this is, okay, you can put that in a perfect way, and this proves that there exists a trace of gamma A at, which put each of omega A dxn into L2 of sigma 0. Okay? So, at the end of the day, this space V of omega is perfectly defined due to the fact that the traces have a meaning. And this problem here, this is an Hilbert space, and this problem here has a unique solution. Okay, now I can I can give the homogenization result. The homogenization result is to pass to the limit in as epsilon tends to 0. And for that, I need a notation that I gave the first day, but that I recall now. Okay, when I have a function VA epsilon, which is defined in omega A epsilon, I define a function VA epsilon twiddle by VA epsilon twiddle equals VA epsilon in omega A and 0 in omega A minus omega A epsilon. So this is the extension by 0 of a function defined in omega A epsilon to omega A. Okay, and if the function VA epsilon belongs to L2 of omega A epsilon, then VA epsilon twiddle belongs to L2 of omega A. The homogenization theorem says the following. This is passing to the limit in the Bruch-Neumann problem. If U epsilon, let U epsilon denote the unique solution of the Neumann-Bruch problem in omega epsilon, and let UA, U to be the unique solution of the homogenized problem, then for the whole sequence, we have the following convergences. UA epsilon twiddle converge to theta UA in L2 of omega A weak. The gradient of UA epsilon twiddle tends to theta, gradient. Okay, the vertical derivative of UA multiplied by the vector zeta in L2 of omega n weak. Okay, so this is a vector in L2 of omega B, A, A. This is a scalar in L2 of omega A because this is only the last derivative of UA. This is the density of the teeth in omega A, and this is the vector zeta that I introduced before. Okay? And for the below part, U epsilon B, UB epsilon tends to UB in each one of omega B weak. Okay, so this is completely standard and expected. This is a little bit unexpected. And all the whole sequences converge, and the result are theta UA and theta vertical derivative of UA multiplied by zeta. Okay, so the result is, in brief, the limit in weak topologies of the weak limit of the Neumann-Bruch problem in omega epsilon is the homogenized problem in omega. Okay. Note that we choose a strange thing to denote by theta UA and not by UA the limit of UA epsilon twiddle. And this has great importance in what will follow. Now, the corrector result. The corrector result is something which is stronger than the homogenization result because we begin defining reminders, and the first reminder is just to take this is the definition of rho A epsilon. We define rho A epsilon by the fact that we can write UA epsilon twiddle, which is a function in L2 of omega A, as the characteristic function of omega A epsilon multiplied by UA. And I didn't say that in what I wrote here, so I write this here. UA belongs to L2 of omega A. And here, dxn of UA belongs to L2 of omega A. And all of that is already known because UA, as I said, is in L2 in each of omega A dxn. Okay, so here we have a function rho A epsilon, which is the difference of two functions in L2. So this is an element in L2. Okay, here the same, the gradient of UA epsilon twiddle, which is a vector, is written as the characteristic function of omega A epsilon, the vertical derivative of UA and the vector zeta, and this is the definition of sigma A epsilon. Okay, the definition of rho epsilon B is simple. This is the difference between U epsilon B and UB. The vector sigma B epsilon is the difference between gradient UB epsilon and gradient UB. Okay, and the corrector result asserts that all those four function or vector tends to 0 and L2 strong. Okay, so this is more than the result of homogenization, because in the result of homogenization, we said that UA epsilon twiddle tends to theta UA, okay, in L2 weak. Here, we write that UA epsilon is equal to the characteristic function of omega A epsilon multiplied by UA, and since key A epsilon tends to theta, weakly star, we see that this term here tends to theta UA, but the weakly in L2, but the remainder, which is here, tends to 0, L2 strong. So that means that we have a representation of the solution UA epsilon tilde, just taking this UA epsilon tilde equals to UA in omega A epsilon and 0 outside, and the remainder tends to 0 strongly. This is a much more strong result. Okay, I now pass to the proof of this theorem. Okay, let me have a look. I have more or less 15 minutes. So I hope to succeed proving at least the homogenization theorem. Okay, so the proof of the theorem is very easy. It consists, it's a classical thing. We use a test function, we obtain an a priori estimate, and then we extract a subsequence. We do that in the first step. Okay, so recall that the formulation of the brush problem is the following one. U epsilon is in each one of omega epsilon. And for every V epsilon, sorry, here there is some epsilon missing. For every V epsilon in each one of omega epsilon, we have the equation in the variational form. Okay, I will take V epsilon equals U epsilon in this formulation. If I do that, I will use the coerciveness and to say that this term here is bigger than alpha, the integral over omega epsilon of gradient U epsilon square. This is standard. This term here is, when with U V epsilon equals U epsilon, is bigger than gamma, the integral over omega epsilon of U epsilon square. And here I use Young's inequality. This is less than 1 over 2 gamma the integral of f squared in omega epsilon plus gamma over 2, the integral over omega epsilon of u epsilon squared. This term here is, okay, we make the difference and we get that this sum here will be less than this value here, but I can, in the right-hand side, augment this constant just by taking 1 over 2 gamma, the norm of f in L2 of omega and no more of omega epsilon squared. And I get, using the twiddle, which consists to replace omega epsilon by omega at the price of putting a twiddle on u epsilon and of the gradient of u epsilon, I get this inequality, which says that the that gradient u epsilon, gradient u a epsilon twiddle u a epsilon twiddle are bounded in L2 of omega to the power n, L2 of omega a to the power 1, and u epsilon b is bounded in each one of omega. So this is the a priori estimate, which is very close to the classical a priori estimate that you have multiplying using u epsilon as test function in the equation. Except that here we have to extend u epsilon in A, in u epsilon A twiddle, and gradient u A epsilon in gradient of u epsilon A twiddle. Okay, so we can, since we are bounded, we can extract one subsequence that I will still denote by epsilon, such that those three functions or vector converge to something in L2 weak, in L2 of omega to the power n weak, and in each one of omega b weak. Okay, so as far as u b epsilon is concerned, I will denote by ub the weak limit of for this subsequence. I will denote by ub the limit of ub epsilon. For as far as ua epsilon twiddle is concerned, I will denote this limit by theta ua. Okay, this is a strange idea at first glance, but this is a good idea. Okay, first of all, this is perfectly okay because theta is a function which is in between theta 0, which is strictly positive, and 1. So, okay, when I have a function ya, which is in L2 of omega a, I can define small ya by capital Ya equals theta small ya, and small ya is in L2 of omega. And this is due to the fact that theta is greater than theta 0, strictly positive. You understand that when theta can vanish, this is a little bit more complicated, hence a new work, which is a good thing, but okay, but which needs some effort. Okay, why to do that? Why to denote by theta ua the limit of something which is ua epsilon twiddle? Okay, there is a good reason for that. Okay, let me consider a function w in L2 of ua and define ya epsilon by as w in omega a epsilon. So this is the restriction to omega a epsilon of this function W, which is in L2 of omega A. Okay, in other words, y omega A, y A epsilon twiddle is exactly the characteristic function of omega A epsilon multiplied by W. And this function converges to theta W in L2 of omega A weak. Okay, hence this notation. Okay, and same thing, I define the vector xA not as the limit of gradient U epsilon A twiddle, but okay, as the limit in L2 of this thing divided by theta. Okay, recall that theta is the density of the teeth in omega A, and not that UA belongs to L2 of omega A and CA is a vector in L2 of omega A. Okay, very good. I can also pass to the limit in the equation. So at that point, I have extracted a subsequence, and I can pass to the limit in the equation which was here, written here. But now I will take V epsilon equals V fixed for some V in each one of omega, and note that when V is in each one of omega, V epsilon is its restriction to omega epsilon is in each one of omega epsilon. So I can put V epsilon equals V in the equation. And then if I'm doing that, I get the following result, that for every V equals VA, VB in each one of omega, the equation becomes the integral over omega A of gradient U epsilon A twiddle gradient VA multiplied by A, the same thing here, C U epsilon A twiddle VA integrated on omega A. Okay, those terms are not touched by this. And here I have to replace the integral over omega A epsilon of F VA by the integral over omega A of the characteristic function of F VA. Okay, now it's easy to pass to the limit. This term, okay, sorry, this term converges to theta xA here. This term converges to theta UA here. Gradient U epsilon B converges to gradient of UB. U epsilon B converges to UB. Okay, this term is fixed, and this converges to theta. Hence, we have passed to the limit in the equation with the new variables theta xA and UA and UB here. Okay, perfect. Okay, next step. This is a reminder of what we did. We extracted and we passed to the limit in those three sequences in L2 weak with UA, CA, and UB, which belongs respectively to L2 of omega, L2 of omega power n, and in each one of omega. And we have the equation that I described just before. Okay, now I pass to the second step. And the second step is to prove that the vector xA that we introduce in the previous step here, this vector xA is actually nothing but xAn is last component multiplied by the vector z. Okay, and that A xA is equal to 0 A0 xNA. Okay, so this is this is the most striking point in the proof, because we are able to identify the first important point in the proof. We are able to identify the vector xA when we just know his last component xan and the vector zeta that I said is defined only by the matrix, from the matrix A. For that, we use special test functions, which were introduced by Robert Brizzi and Jean-Paul Chalot in their PhD thesis in Nice in 1978. Okay, by the way, the paper was published in a regular journal only 20 years afterwards. But the thesis was perfect. I was a member of the committee. Okay, so those functions are made in the following way. They are defined here. We fix some epsilon. We fix a vector lambda prime in Rn minus 1. And we fixed an index J in the set of index J epsilon. And we work in the cross-section of the one tooth, which has omega prime J epsilon as cross-section. And in this cross-section, we define W epsilon prime epsilon lambda prime of x. This is a function which depends only on x prime, and which is defined as the product of the vector lambda prime in Rn minus 1 by x prime minus a point of the cross-section, where this point is any given point in the cross-section. So let's see the picture. Okay, we have a tooth here. Let's take this one. This is the tooth which is of interest for us. Okay, in this tooth, we define a function W epsilon lambda prime, which is the following one. It is 0 in the center, in any point, in a fixed point of the tooth, and it has the slope lambda prime. Okay, so we do that in every tooth. Okay, and also in the tooth which are adjacent. So this is the function W lambda prime epsilon. This function has a slope lambda prime in each tooth. Okay, very good. Those are the functions of Brizzi and Chalot. Okay, so what are the characteristics of those functions? First of all, those functions have always a slope in each tooth, the slope lambda prime 0, because they are function. Okay, so their gradient in the tooth, for every point in any tooth, so for every point in omega epsilon A, the gradient of the function is lambda prime, is the vector lambda prime 0. And the function is less than epsilon. Why? Because we make a very simple estimate here. We estimate this. We estimate the absolute value of W by the length of lambda prime and the length of this difference, but this is less than epsilon since all the 2 points are in the same teeth. the same tooth, and every tooth has a diameter which is less than epsilon. Okay, so okay, this function is in C1 of omega A epsilon and in each one of omega A epsilon, and its gradient is always lambda prime. So we have defined a function in each one of omega A epsilon, which is not continuous on omega A, because when the function, the teeth are adjacent here, okay, the function is not continuous. But this is not a problem. This function has to be defined only in omega A epsilon and not in omega A.
François, okay. We should stop.
Okay, give me just the time to arrive at the end of this thing. I need, okay. Okay, so I take any function phi in C infinity with compact support of omega A, and then the product of those two functions is in each one of omega epsilon, and I will use it as test function in the equation if you give me some more time, or if not, tomorrow. Thank you.
Merci, François. Yes, maybe we stop here. You will go on tomorrow. There is a question. Somebody who asked what will be the outward unit normal of omega epsilon if two teeth of the brush have the same boundary.
So if I understand, okay, I cannot see the question because the
okay,
the
I will repeat.
Okay, but I cannot see the chat of my tablet. But if I understand, what is the normal? What is the exterior normal to the boundary d omega epsilon when the boundary is not smooth?
No, when the two teeth have the same boundary, so two teeth touch each other.
Okay, look at that. Where is, okay, look at this tooth. Okay, how is the normal? The normal is here, and the normal is here. Okay. Okay, so let me look at this group of three teeth. The normal for this teeth, the exterior normal is here, and the exterior normal is here. There is no problem to define the exterior normal. The problem is not this, the normal in 2 dimensions is perfectly defined in every point. Okay, and this is like that. This is, okay, there is a problem when you look at in dimension more than 3 or equal to 3 to the normal to omega epsilon. Okay, sorry. To omega prime epsilon. Okay, sorry. Omega prime j epsilon. There is a problem because this set is not smooth, so there is no normal. Okay, but I don't care about the normal. I said that I will use only the variational formulation, and that the partial differential equations with the Neumann boundary condition written in the usual sense is just an image for that. When the set omega prime g is epsilon is smooth, this is the usual normal, and this is the usual boundary condition. Did I answer the question?
I don't know, I think so. Let us wait the answer. In the while, we have a last question, which is what of the matrix coefficients, what of the matrix coefficients is oscillated? Do we need some strong convergences on the solution?
Okay, this is another problem. Okay, so if if the matrix is fixed, okay, the problem is solved, and I explained that. If you take a sequence of matrices A epsilon of X, which are uniformly bounded, uniformly coercive, and converge almost everywhere, this is a good exercise for everybody to see that the same proof will work without any problem. The problem is when you make homogenization at the same time. We didn't do that at the moment, but we plan to do that in the next future. So homogenization plus brush, plus the geometry of the brush, at the moment, we don't know. But we will know probably very shortly.
Okay, thank you very much. There is just a remark from Renata who said that maybe there is a C in the statement of the homogenized problem. So maybe you can check before sending the slides. I don't understand, but okay. I think we should stop here because soon we will have the talk of Danielle. Thank you very much.
Okay, Patricia, I still have 2 minutes because it's not 10:40. So
excuse me.
So let me say that my slides are online. All my slides of the 3 lessons are already online on the page talk. Sorry, on the page talk of the website of the conference. Okay.
Okay.
So okay. I think that this answers the question of Renata. And by the way,
Renata said that there is a letter missing in the statement, like some C. But okay, after maybe you can read the conversation, or I send you a mail with that remark.
No. Okay. Don't worry. I will read it and I will answer Renata immediately when I see the things.
Okay. Thank you very much.
Thank you. See you tomorrow.
See you tomorrow. Okay. Bye.
Bye-bye.